Okay, so I think we had a great session last time with bio, and what I'm going to do is I'm going to essentially try to pick up from where he left and bring in a similar exercise to what he was doing, slightly different, but more or less the same logic as we explore the topic of generative design. So I think I have the slides that you used last time in bio, so I'm just going to pick out from them and then explain my story as we go along. So I think you spoke about this. I'm not going to go into it. Then you explained what generative design is all about, and you gave some really good links and videos and some resources for everybody to go have a look at. And then what I'm just going to focus on is this slide when you're talking about the anatomy of a generative design process. So the exercise I'm going to do today is very similar to what bio was doing in Dynamo. I'll be using Rhino and Grasshopper to create a similar, let's say a twin of that exercise. And what I did is I just tried to follow the steps indicated here to build the same logic and show that despite using, or even though bio was using Revit and Dynamo and I'm using Grasshopper and Rhino, the thinking behind the logic is largely the same. So it's different tools, but how you address the problem is quite similar. So I tried to offer responses to this, I think the skeletal frame of the design process. So what I came up with is a very simplified approach. What we're going to look at designing is an office tower in an urban context. So that is basically the what of it. And we're going to use geometric parameters like the length and the width of the building and the height, etc. It's geometric parameters, and we're going to try and rotate the building a bit. I think everybody likes a twisting tower. So we're going to try and twist it around to see what that means. And then we also then define the range of the parameters. And what we basically want to do is come up with an office tower which has great views in an urban context. So I think bio, you also looked at views again in your script last time.
Yes, indeed.
Yeah. Yes. So I think that's where most of the similarity is. Then the success will lie in the quantity of the views that we're getting, and of course, if we can get a higher density, then it means the developer is going to make a bit of more money, which is a win for everybody. And then what we are going to be maximizing is the view percentages. So that's the core of it. And I think as I go through, you sort of get to understand what's happening. So I think maybe I can just show you. This is basically the context of how this problem is going to be addressed. So we have a tower here, which is situated in between a number of blocks. And then we are trying to do view analysis for number of points, or like a grid of points inside each floor plate, and trying to see how the buildings around our design, our tower, are going to affect how much the views you get at every point. So this is a very abstracted problem. When you're going to handle this in real life, it's going to be much more complex than this. And there's an assumption that this tower is an entirely glazed tower. So you don't typically find that in this part of the world, but we can assume that is how it is for now. And I think that's the key assumption. So I'm not sure if we have a fully glazed tower in Cape Town. I would guess not, but
We have Portside. by DHK?
Oh, yeah. Exactly. We have one of them here. So, yeah, so there's a case for it. But anyway, I'm going to bring up my script. So what I'm going to do is, before you even go into the viewport in Rhino, I'm just going to explain what the script does. I'm not going to rebuild it because that's going to take some time, but I'm just going to explain the general logic of how the script works. So at the beginning here, we are defining the site through a very simple piece of code there. Then we are subdividing it to create a number of blocks which comprise a super block. And then we define the context blocks here. I'm going to come back to this and explain how it all works, but at great speed. And then here we have the parameters of the actual block that we have. So we have the height of the building, starting from 90 meters to, I think, 120 meters. So it's a fairly tall building. Then we have the length of the building and its width. Then this is constant, like the floor-to-floor height. And then we have the rotation angle. So the sliders you see highlighted in that reddish color are the parameters that are going to be used for creating our generative design space. And then, so this bit of code is going to create the form of the tower and twist it. And then out of that, we can also look at getting one of the sides to form part of the context. So that's an assumption that a building is going to be fully glazed on 3 sides, and then one side is opaque or something like that. But it's not really important for this exercise. And then we are going to extract the floor plates, because we need to find on every floor what is the view condition on that. And then every floor plate, we're going to extract the area of the floor plate so that we see, we can then add all the floor plates to see what is the gross floor area of the building. And then this is a script which uses Ladybug tools. It calculates the view percent. So it basically checks out for whatever you throw at it, how good the views are, and it gives you like percentages of the views on every test point that you have. And then after that, we extract some information in terms of the maximum average views over the entire building, and then the minimum views, like the least minimum and all that. And then from then we extract some geometries that we want to use for visualization. So that's basically the script. And then we are going to use Wallacei to do the optimization. So this is where the design space is tested. I can't remember the algorithm that you used for your presentation last time, Bio. What algorithm was it?
It's the NGSEA2. NGSEA2. That's the Autodesk algorithm.
Okay.
Yeah.
Okay. Yeah. So Wallacei is driven by an NSGA2 algorithm. So I won't go into the details of how these algorithms work, because I'm not like a pro on that. I just understand how to use them, and again, it also takes quite some time. And then from this exercise, we'll then decode the phenotypes. We'll try to bring back the geometries, the solutions that we found, to bring them back into the viewport. So that's the anatomy of this script. And now I'm going to maybe start to go with it from the beginning. So let me try to bring out these guys. So that's our site. It's a 200 by 200 block. And from there, we find the center of that. We're going to use that centroid for something later on. Then we divide that site into a 3 by 3 grid. And then at the center of each of these points, each of these squares, we're going to create our tiny blocks there. So that's the footprint. Those are the footprints of the blocks, and how I did that was just simple rectangular, creating a rectangle component there, and then we create boxes out of those rectangles. So these boxes share their parameters are coming from a gene pool component, which is basically going to give you different heights of the blocks of the boxes. So if I do that, let me not show anything there, preview off. So if we do that, you can see that we have our boxes here. So if I change any of these, you can see the boxes are responding to those genes, because this is what's determining their heights. Right. So once we have these boxes, they are going to become the context for the building surrounding our tower. Then we begin working on the tower itself. So the tower is defined from this point. We have a rectangle there, and then that rectangle, we're actually using these parameters, the width there and the length, to define how big that is. And then we create again a box based on those parameters. So I think this is pretty straightforward. In the box that we define, we then use this cool native Grasshopper component. You find it under the transformations, under the morph subset. So it basically twists whatever you throw it. So we're twisting this box to come up with that box. So once we have that, that is what we are using to define our tower. So these parameters here are going to affect that tower in terms of the rotation angle and whatever the geometric parameters are. So if we crank this up and make that 120, and then we change the rotation angle and make it totally 90, then we have something like that. I think we have seen a couple of buildings like that by the grades. So yeah, so these are the parameters that define the geometry of the building. And once we get to this stage, what we then do is we are going to identify the floor plates. So there's this component which creates contours. It's basically going to create sections on the tower. Let me hide these guys so that we only see the tower here. So this component, what it does is it takes some geometry and then it creates section lines, literally, at a defined distance. So this distance, we're getting it from this component, which is giving us the floor height. So it's a constant of 3. So after every 3 meters, you get a section line throughout the entire form of the building. And then when you get your contours, you convert them to become floor plates, which is just turning the curve into a surface. So if I preview this off, you can see now that I have a number of floor plates, which are coincident with the floor, the levels where the floors are going to be. And after doing that, what I then did was, this is the floor plate. So this is, you can think of this as level 0, like the actual finished floor level. So if you assume that someone is sitting, you could say maybe their eye is at a certain level, whatever level you decide that to be. So I then moved those surfaces up to try and simulate the position where someone is sitting. It's not really important, but it just gives you an idea to say, I mean, if you're going to design for views, then you won't really have many situations where someone is lying on the floor. Chances are someone is sitting or standing. So you want to test for views predominantly at those levels. And if we even go further and try to articulate this building more, and then our assumption right now is the building is fully glazed, but typically you find that in every high-rise building, you get maybe from the finished floor level to around 900 millimeters. Maybe it's an opaque surface, and then you have your glazing starting from that level to like 2.1 meters, 2.4 meters, or whatever it is. So it's important then to set the parameter of this height so that you have a situation where at least you're trying to simulate something which is closer to reality than not. So once you get this floor plate, here I was just doing a few things to cull the last one, which is actually the floor plate at the roof, because you don't have, typically you have the last floor and then you don't need to calculate views for the roof because you're already outside the building. So I think we can follow. What I'm going to do is I'm going to activate this component so that we have an idea of what the building shape always looks like. And then after extracting all our floor plates, we then use these components to find the area of the floor plates. So we're going to get 39 values. If I throw out a panel here, you'll see that we have 39 values of different floor plates, their areas. They pretty much seem to be similar. It's just that they are slightly different because of the twist. Then we add them all up using a mass addition component, and then we get this value, which is 42,000 square meters. So this is a key metric that we would want to look into because it represents our gross floor area for this tower. Then we also have our context geometry. So maybe I could do this right now so that we also see that. So we have our context like that. Yep. And then after this, this bit of script is what's going to give us the views in our analysis. So maybe let me maximize here for now so that we have a look at what this does. So basically, we have these two components. This is the component that does the stuff in Ladybug. These components here are just going to help us visualize. So it's a visualization tool, so I'm not going to go into it much. What's happening here is we are getting a view type. So there are a number of view types you can test for. If I do that, you see that there is a list of 5 of them from 0 to 4. So if you have horizontal radial view, then the 30-degree offset. So this is the one that corresponds to like human peripheral vision. So that's the one that I'm going to use. So you can see that on the slider it says view type 1 because that's the selected one. So there are a number of them, but this is the one that I chose to use for this study. You could try different views and see what you get out of that. And then here you can specify the resolution. So the higher values will resort to more accurate analysis, and it also takes time to get to that. Then the geometry that you are going to enter there is the geometry that you're going to run your analysis on. So we are using the test levels, which is basically those elevated floor plates at 1.2 meters high, or whatever it is. So that's the geometry that we're going to test. If I do this, and let me preview that. So yeah, it's the same component. So these are the test levels that we're going to be analyzing. And then the context, you basically use the geometry that you have around your building. So these are the buildings, or this is whatever geometry is going to block the views from your test points. And to maybe make it easier to visualize, I'm going to show you a specific point. So we have quite a number of points which we are studying. I think all in all 4,200 points that are being analyzed at a grid size of 3 meters. So I did this at a very cost resolution so that it doesn't take a lot of time and it just illustrates the point. You could make it much finer, like 0.25, then you get much finer results, but it just means this value here, which is the time you take to run your simulation, is going to increase. So you have to kind of make a call depending at the stage of design where you are to say how fine do you want your resolution to be. So if I move into that point, let me try to do that and then zoom into it. So what's happening is this type of study, it's called the horizontal 30-degree offset. So at each point, it's going to give you throw around like isovets, or try to find vectors of lines of sight from that point to see how far these lines go without an obstruction. So if it is an obstruction, it means that the view is blocked at some point. So if you test different view types, if I change this to 0, you see that that becomes a different view type where you're looking at it at a horizontal level. If I take another type, you see now this is in a spherical study, so it takes vectors in every direction. If I do that, it only takes vectors from the horizontal plane going up. And if I do that, it's slightly different, I think. But yeah, so this is where you define the type of study that you are going to go for. Okay, so that was just one point. If I visualize all the points here, you can have an idea of how many points we have. So these are all the points that have been studied for this simulation using the resolution that we specified at 3 meters. So it's quite a dense study. So if you push this resolution higher, it only means that it's going to take time because we are throwing at it a much finer study. So that's the price you pay, unless if you have a very, very good, extremely super PC. So after that, you set this to true. So when you set that to true, then the simulation runs and it's happy days. And then out of it, you get the view vectors, what I was just showing you now. You get the results, which is basically a list of numbers that align with the points that you have given to test. And for each point, you get a view percentage. So when you have that done, what you're going to get is something like that there. It gives you the title of the study that you're doing, and it gives you like a legend to say, so this is 28%, and so you're ranging from 28% to 84% views. So the blue is going to represent areas where you have very good views, or the most, and then the reds, or whatever the color is, it means those areas are not as great. So let me try to show how that's going to work. Let me switch everything there off so that we can only see what's happening here. Preview off. Okay, maybe we'll need this one to stay on. Yeah. So if I, yeah, that is on, is fine. So if we start changing this context here, let me try to do that. Sorry, I'm using a very small screen here. So if we start changing the heights of these towers, you can see that is going to respond to that. For example, if we bring all these towers down, I'm not seeing any change here. I think I have some other information previewing off. Hang on.
You maybe have to rerun it, Gerald, like that play button thing.
Okay, let me run it again. There's something that I'm previewing which is blocking my views here. Test levels. Okay, let me do this. Right. So I'm going to try and bring up the levels, and then we can see the changes too on our tower there. Or maybe what I can do is, yeah, anyway, let me try to run them and see. So if I start increasing these heights, let me max all of them to 120. I think we can focus on maybe the top floors. You can start to see that we're getting more greens here. I think maybe, yeah, these two blocks are going to affect this one much more. So pay attention on where the greens are. I'm not sure if this is helping me previewing those meshes. Maybe it becomes clearer if I do this. Or if I change the height of the building to make it shorter, then I think that's also going to affect the simulation. Yeah, I think it becomes much more visible. So the building is responding to how the context around it is affecting the views. So yeah, so by doing that, you need to randomize this. It looks terrible. If you have buildings that are all the same height in a city, it's almost criminal. So yeah, so that's how the view analysis works. And then when we get that sorted, when that works out, we then extract the geometry. So the geometries we're taking out is the mesh. The mesh is basically the mesh that you see inside the tower, the mesh of the results, and then the legend, which shows you the minimums and the maximums and the range in which you find that. And we measure that information, and then we also take the context geometries, we slot them in to create what we are going to refer to as the phenotypes, which is basically the geometries for every solution that we're going to test. And we also get an average of the results. So on these results, if I take a panel out here and I take my results, you'll see that for all those test points, I have a value. These are different percentages, 62, 60, 63, you know, all those percentages. So we can find an average for that. And then we can also find the minimum and the maximum. So the maximum here is 88%. It makes sense because if you look at our legend, it's coming up to 88.43, the bluest point, and the minimum is 28%. So it's also that. So that's the minimum and the maximum. So what we want to do is we want to try and find forms of this building where the minimum, the minimum view, so the point with the least views, we want to try and find a form which gives us the maximum minimum percentage. And then we also want to find the form that gives us the maximum average percentage of all the points. Because when you chase after just the maximum only, you might find shapes where certain floor plates have really good views, but then the rest of the area is not really great. So it's you have to kind of decide which metrics you want to really focus on for your analysis. So these two are some of the objectives that we want to see what to maximize. And then the other objective that we wanted to maximize is the gross floor area. So you can see that these components, these are all native Grasshopper number components, but they've been given a prefix WLC, which basically stands for Wallacei, the solver that we're going to use, this guy here. And the ease of that is when you prefix them with those letters, it's easy to find them on the canvas using Wallacei. So you can just select all sliders, then it finds them. Select all objectives, then it finds them. And then the parameters that we are using to define the form of our building, which define the design space, these are going to be the genes for the analysis. So we have the genes, which is basically the parameters we're changing, the objectives, which is the metrics that we want to focus on, and then the phenotypes, which is the shapes of the context and the shape of the building itself for every solution that we are going to iterate over. And then after that, this is post-processing, trying to bring back the results into Grasshopper and Rhino. So I'm going to, I already did I already ran the solver earlier on today, so I'm not going to do it again. I'm just going to go through it so that we have an idea of how it works. So when you start Wallacei, so if you double click this guy, you get a window which pops up like that, and it basically has the settings, the first tab where you have settings, then you have the second tab where you have your analytics, then you have a third tab where you have the selection of solutions, and then this is a link to the Wallacei forum, and then this is a link to the Wallacei primer, which is like a document that they have, a PDF document which explains how this guy works. So when you go to your settings, you have to define the study that you're going to do in terms of the sizes of the generations that you're going to run when the algorithm runs, and then the count of each generation. So here we have 100 generations, and each generation is a size of 50, so we get a population size of 5,000. And from then you have your algorithm parameters. So I think if you go through the primer and kind of get an idea of how this works, it would be useful. This is basically how genetic algorithm works. They're trying to create, to look for genes which give you good results, and you are optimizing for multi-objectives. So it's going to be a conflict of objectives to try and find the best conditions for each of them. So you find that one solution could be really good in objective number 1, but not really good in objective number 2, because you always have competing objectives. And then so if by setting these parameters, they give us certain depth to our design space, and they give us certain times in terms of how this is going to run. So the parameters you see here basically are extracted from your Grasshopper file. So it's saying the number of genes. So the sliders that we're using, we have 4 sliders, which speaks to these genes that you have here, which are these 4 guys that you have here. So that is what this is talking about in terms of number of genes or sliders. Then the number of values. So if you take all the values that you have from those sliders, you come up with 50 different values. and then the number of objectives we have is 4, and then the size of the space, the search space is like, that's 21,000. So a lot of possibilities on that. And then these are just visual cues you get as the simulation is running. And then after that, once you're happy, you start it. So I'm not going to start it, because if I do, then it's going to overwrite what I already did. Then when that is done, you can then draw the entire population, and you can see the population that we tested, our 5,000 population. So it's also pretty difficult to explain this objective space, because here you can see we have 3 axes, right? But this is actually a multi-dimensional problem, because we have 4 fitness objectives. So when you're plotting these objectives in 3D, it's a bit tricky to visualize it, because when it's a multi-dimensional analysis, you can't really visualize it easily with your mind, the same way we visualize geometries and forms and all those things. So you start this, and then the simulation runs for some time, and then after that you can then do your analysis. So when you do your analysis, you get these interesting graphs there. You get some standard deviation graphs which show you how the solutions evolved. Then you also get fitness value charts. So yeah, what you can see there. But what you can then do is you can also identify certain solutions. So if we look, say, for fitness objective number 1, and we look for rank 0 and we select it, it shows us here gives us this multi-objective chart, and then you can see the solutions that you found in that case, like how it performed in terms of the different fitness objectives. So we have objective 1 to 4, and then it shows you, since this is ranked 0, it means it's the best solution in terms of objective 1. So it's very close here to the center. And it also did fairly well on objective 4 and objective 2, but not so well on objective 3. So this is the highest ranking solution for fitness objective 1. And then it just highlights that dot where that lies on all those graphs. And then if you go for objective number 2 and you select that, you see the solution that corresponds to that. So it did really great on objective 2 and 4, not so great on objective 1 and 3. And you can see the ranking here. So on objective 2, it's ranked 0, which is the highest. Then on objective 4, it's ranked 578 out of 5,000. But on objective 1, it's 4,200. So it's almost towards the bedside of objective 1. So that explains how you can basically see these different solutions. And then in terms of selection, there are a number of ways to select them. So when you select some solutions, as you can see, I have selected solutions here from some generations. So I took generation 0, 20, 30. This was just random selection. And then I exported them to this export list. And then this is the stuff that then I bring back into Rhino. So you have different ways of selection. You can use the parallel coordinate plot settings. So when you do that, you get like 4 methods, different analytical methods of bringing different solutions to that. If you get, say, the repeated fitness value, it will give you the most repeated, it highlights the most repeated. Let's say we take objective 1 and say give us the most repeated fitness values, and you run that analysis. It will show you the most repeated values on objective 1. So the bigger the circles there, it means that's where you get the most repeated values there. If you pick for objective 2, and you do the same, it gives you again, so you can have an idea of where the most repeated values were lying per objective. And then you can also do solutions with repeated fitness values, so it extracts the associated solutions to that. Then you can have like the relative difference between fitness ranks, and so on and so forth. Then you can also use unsupervised machine learning, k-means clustering, to cluster different generations, for example. So when you cluster, let's say generation 90, and you run, okay, so I've run this already, so I need to change that. You could say, let's identify generation number 5, and then say we want it to have 3 clusters, and then we run that. So here you will see that it has tried to cluster them using k-means into 3 groups, and then it ranks them again here, where you see clustering. You have cluster 1, cluster 2, cluster 3, and then all are coming from generation 5. That's why you have this G5 over there. And then these are the indices of the solutions that were identified. So it ranks them basically with using the distance from the center of the cluster. So you can use k-means clustering on some generations or on all generations, or you can use different machine learning approaches like hierarchical, all those ones. You have to understand, obviously, what they do to know how to use them well. Then you can also use Pareto front solutions. So this is basically just recreating the Pareto front solutions, and in this case, it's going to pick from the last generation that was used, which was 99. Or you can also select specific generations and bring them back into your viewport. So generally, how these algorithms work is the last generations typically have like really good solutions, because the algorithm has been running for a while. So what most people do is they just go and check the last generation as a benchmark, and then they try to use other analytical methods to find different solutions that they can also add to the export list. And then when you export that, you are going to get back your geometries coming into Grasshopper as your phenotypes. So at this point, I'm going to hide everything here so that I can only focus on what we get out of Wallacei. So I'm going to enable this bit of script here, and then I'm going to preview that, and I'm going to preview that. So this is one solution that I have there, and I think if I can check out, this is actually generation number 20, solution number 21, if I'm not mistaken. Yeah, so it's Wallacei phenotype generation number 20, individual 21. So I have about 335 phenotypes that I brought back. And then if I change this slider, you're going to be seeing the different solutions. The geometry is not changing, the context isn't changing because it's the same, but the different towers are changing based on the solutions that you got and brought back into Grasshopper. If I'm going to enable this guy, it's going to also give us like the fitness chart that you see here. So this is similar to what we were seeing in Wallacei when we were doing this here, but it has been brought back to Rhino for just ease of visualization. So this is a this phenotype is again, we can see it there. It's generation 0, individual 3, and then it shows you again here generation 0, individual 3, then fitness rank and fitness value for objective 1, 2, 3, and 4. So this is then stuff that you now use to explain your design case to your colleagues or whoever is interested in this design study. You can also preview all the phenotypes using this component, but this component is power hungry. As you can see, I wrote it there on my script. I'm going to try it, and you guys can pray for me. It's going to import all 300 of them. We actually have 5,000 in the simulation, but I only chose like a subset. So yeah, so let me preview these guys off because they are representing just one thing. And then if I do that, you can see that we have number of exported solutions, 326 out of 5,000. Oh, my computer is starting to move really slowly. Maybe we can test out another view there. Not a great view, maybe. Yeah, there we have. So this becomes like the geometry of all the different conditions that you have used to test. So I think in a nutshell, that's how Wallacei is going to help you do generative design. Let me disable this guy because my computer will complain. But I think you have an idea of how this is all working. So let's bring these guys back up. Right, and then we zoom back to that. So yeah, guys, I think let me end it there because I'm seeing my time is bad and they might not have time for Q&A. But that's the gist of it.
Jeez, thank you so much. That looks very cool. I must say, Wallacei it seems like it has a lot more customization in it. You can go really deep into the algorithm, it seems, compared to the Autodesk interface.
Yeah. I think it's quite intense. I've been using it for some time now for different things. So I think the last time we were doing something in Karamba in Kangaroo, right?
Mm-hmm.
Yeah. So I think there's actually an example that the Wallacei guys did for something similar, and they really pushed it hard. So you can get quite, especially if you understand the theory of how these algorithms work.
Yes.
You can actually take them on quite further and quite deep. Yeah.
Okay, and is Wallacei only for optimization? Can you do randomization studies, or like with the Autodesk one, it has cross product, which means it finds every possible solution.
Mm-hmm.
And there's also one that's called like this, which means like you pick one of your solutions and it runs similar solutions to that one. So is it just an optimization tool, or can you do other things as well?
Yeah, I think you can. I wouldn't know about randomization because I haven't really tried to do that. But in terms of similarity, yes, you can identify. I think I was talking about solutions with repeated fitness values. So you can find averages across different objectives, and then you can also find similarity across different solutions.
Okay.
So yeah, there is quite a lot you can do with Wallacei. But yeah, maybe we would have to compare with the Autodesk version that you used to see. Probably someone wrote about it anyway to say
probably
what are the differences. So it should be possible to find, all those different approaches that one can use. Cool. And it's not the only solver that I particularly like Wallacei because of its customization, as you mentioned. But there's also Galapagos. Galapagos it's only that it can't do multi-objective optimization. Yeah. But Galapagos, there is also Biomorpha, I think. There is Octopus, which also does multi-objective optimization. But I think Wallacei is a bit more intense in especially even the UI itself, it allows you to tweak so much about the stuff you're doing.
Not a very friendly UI, I must say, but it does.
Yeah. It's a bit intimidating, but they did a really good YouTube tutorial playlist on how to use it.
Okay.
So once you just get over that, you see that it's really, really straightforward.
Okay, we should probably include that in the video. Maybe you can send me the link.
Oh yeah, absolutely.
That is actually one of my questions. Where you learned this, Gerald? Was it part of your studies, or was it just self-study via YouTube?
Yeah. Like I think I picked it from the Rhino, the McNeil forum.
Yes, yeah.
So I was running some Ladybug simulations, and at one point I realized that I needed to optimize some stuff. And then I started digging around, and then people were talking about Galapagos and Wallacei and things. So it was just snowballing backwards.
Okay.
And at school they didn't really teach us optimization. It was assumed you knew that.
Oh, wow. Yeah. Because that is also just my other question, whether you've actually used this in practice, like for example, maybe for environmental or other or loading, structural, or any of those type of things, or is it because both you and Bio looked at views, but have you used it for other things?
Oh yeah. I've used this for a lot of things. I've used this for energy studies. I've used it for, what you use it for, it's the same thing. As long as you have your parameters, a list of parameters, and some metrics that you want to optimize for the objectives that you have, then it's going to fly. Yeah,
it doesn't really care what you feed it. It's just it's going to optimize.
Yeah. I'm just battling to, imagine what I'd use it for. And the one was environmental, like you mentioned energy now. That's really a good one. But yeah, I was just curious as to the use cases.
I've seen someone use generative design to place views on a sheet, to find the best arrangement.
Almost like a nesting algorithm. Okay.
It's like ridiculous, but you can push it wherever you want. Yeah.
Oh wow. Okay.
Yeah. It's you can pretty much use it for anything. I think at one point I ran a study where I think for my thesis, at one point I had about 8 parameters and about 10 objectives or something like that. And for another study that I was doing for one of our data encoding machine learning classes, I had a whole bunch of objectives, about 9 or 10, I think. So if you think of it, trying to analyze a data set which has 11 different objectives, it's impossible to visualize that. But you can use these tools to do it for you.
Okay.
Yeah.
Any other questions? Oh, sorry.
Yeah, I should probably give other people a chance as well. But just interestingly enough, I find Grasshopper and Rhino compared to the Autodesk products, it's a very bare bones type of interface. And the first time I opened Rhino, I thought, what's this Candy Floss software type of thing? There's a lot of power under the hood, but it looks like it's not a great interface, and a lot of the plugins and stuff are fairly raw. I don't know how else to put it, but you have to know what you're doing to really get the best out of it.
It looks like AutoCAD, but it's so powerful, man.
It's incredibly powerful, and a very, very highly accurate.
Indeed.
What do you call it? Geometry kernel as well. Yeah.
Indeed. Yeah. I was very shocked by the twist node. I was like, what? Because in Dynamo, if you saw my my presentation, I made each floor plate first before doing the loft. The fact that you can actually just push a piece of geometry and it twists it on its own is
this guy
incredible. Here. Yeah, we don't have that in Dynamo. I have to go through so many other steps to get to that. Right?
Yeah. I think the development team behind Grasshopper tools, it's obviously much bigger. So you find all sorts of things, you know.
Yeah.
Yeah, it's a good one. I like it. It makes it so easy.
Indeed. Yeah, I've been going deep into Grasshopper the past few weeks. So yeah, I'm trying to get on Hyper. Start building
Hyper.
stuff for Hyper. Generative design studies for Hyper. So yeah,
Hyper is pretty cool.
Yeah, indeed.
And you can try to get hold of Andrew. He's quite supportive.
So I'm a human. What's he saying?
Yeah, human. Yeah, I'm on their Discord. So yeah,
I saw a YouTube clip of him. He's like quite a passionate guy. He speaks fast and loud and excited all the time.
Yeah, so passionate. Yeah, I've watched all his tutorials on Hyper, and it's very, very passionate.
I'm going to stop recording bio. Before we say bad things about Andrew, and then he will come at me. And
he'll be upset with you.